So we ended last time, and we kind of stopped in the middle here with this unit conversion between moles of calcium carbonate and grams and milligrams. The second question that we were asked here has to do with converting this number of moles of calcium carbonate into formula units. And remember, formula units we can think of as basically the same thing as ionic molecules. So when we're talking about converting to formula units of a substance, we can think of it along the same way as molecules. We know that we're going to need to use Avogadro's number. So starting with the number of moles that we ended the previous calculation with, we know that for every mole of calcium carbonate, it's going to require, or there will be, 6.022 times 10 to the 23rd formula units So the only calculation that we have to do is that conversion, 5.02 times 10 to the negative third, multiplied by Avogadro's number, to three significant figures. We get 3.02 times 10 to the 21st formula units of calcium carbonate. So really that's all that there is to our technique here, is using that organization, using that knowledge of what kind of calculation, what kind of conversion to use in what place will tell us what we need to do and what numbers we need to plug in. So before we move on, are there any questions about unit conversions? All right, so let's look then at an example, understanding that the formatting of the question got a little bit messed up here. This is 10 to the 18th. Not 1018. So we have a sample that contains 2.59 times 10 to the 18th formula units of calcium chloride. How many moles of calcium chloride are present? Now for this answer, for simplicity's terms, I'm going to ask you put it in scientific notation. That way TopHack can evaluate your sig fig use as well. But go ahead and start. in the end, we end up with 4.3 times 10 to the negative 6 moles of calcium chloride once we do that proper conversion and canceling. All right, so relatively straightforward conversion problem here. It's just a one-stepper. Any questions with this particular problem before we move on to another one? So the way you would have typed it into the response should have been like this, 4.30 E, capital E, minus 6. So scientific notation in Top Hat as well as Smart Work goes along like this. If you type in a capital E into a numerical response, it'll automatically bring up the scientific notation, and you just need to type in the exponent there. All right, other questions? That's a good one. All right, let's move on then. Try another one. How many moles of ammonia are present in 24.92 grams of ammonia? This one you don't need to worry about scientific notation. Now, for reference, this is probably an important piece of information. If you do not know, ammonia has a chemical formula NH3. Since we're dealing with masses, you're going to want to know how many nitrogens and hydrogens there are. All right, if it's asking for scientific notation, if you do not have a times 10 to the, your E there would be 0. All right, once again, it looks like we're on the right track. You should have recognized that since we are dealing with grams, we are going to need a molar mass. The molar mass for ammonia we would take by adding together the mass of nitrogen plus the mass of 3 hydrogens. And again, rule of thumb, 2 decimal places is usually sufficient. If you do more, you can. It's not going to hurt anything. You just can't do less. So with that, we get 17.04 as the molar mass. Again, if we consult that graphic, we see that to go from mass of a compound to moles, we're going to need to divide by the molar mass. So that's how our dimensional analysis gets set up. And so when we do that, grams of ammonia cancel, 24.92 divided by 17.04 should give you 2 4 significant figures. 1.462 moles of ammonia, which in scientific notation would be 1.462 times 10 to the 0th, or 1.462 E0. So yeah, it's a little quirk in Top Hat. If you want to evaluate scientific notation, if you want to evaluate sig figs, it requires scientific notation because, as I mentioned kind of early on here, scientific notation always gives you the correct number of significant figures. The number of points in that decimal that you put in there equal the number of sig figs that should be there. Michael? No. So this is more for their algorithm to give them kind of the same starting point. If you know, only use scientific notation if you feel like it's helpful for quizzes, tests, that kind of thing. Now, do you have a question?
Yeah, okay. So when we take the test, I kind of got what you got, but I got one off. Maybe I carry like
1.463.
Yeah, so as long as we set it up right.
Yeah, and so it could come down to also what you divide by. So if you over rounded, if you just gave me 17 as the molar mass of ammonia instead of 17.04, that would affect things slightly. If you use the 3rd decimal place, which I saw some of you did, and it came out like 17.036 or something like that, that would be enough to affect that last sig fig. Because on the calculator here, it's 1.4624. That little bit of rounding that I did that you didn't would be enough to maybe turn that 4 into a 5 and you round it up. So there's tolerance baked in to the answers to accept kind of for those variations. So you should have still been marked correct for that response, because I recognize and they recognize that when you do these kinds of calculations, there is going to be small amounts of rounding difference based on how many sig figs you carry in the conversion, for example. So long as it's not too far off, or if it's not too big of a noticeable mistake, it usually comes out okay. All right, other questions? All right, so let's get into the business of finishing this chapter off. And for that, we need to talk about 2 different concepts. One of those concepts is something called percent composition. Percent composition is really just a way of saying what is the percent of an element in a compound based on its mass. So take, for example, I've got 2 iron oxide compounds here on the board. I've got woostite, which is iron 2 oxide, and hematite, which is iron 3 oxide. From an atomic perspective, I know that it's 1-to-1 in terms of iron to oxygen in the woostite, and it's 1 to 1.5 in terms of the hematite. So we know that from a molar perspective, from an atomic perspective, the iron 2 oxide has more iron in it. But what about from a mass perspective? From a mass perspective, what we need to do is we need to do a calculation. Now, the calculation that we do falls into this category. Mass percent is equal to the total mass of the element that we're interested in, we'll just call it element X for right now, divided by the total mass of the compound multiplied by 100%. Now, we can pull those total masses from a variety of different places. If we're in the laboratory, we can actually measure them out. I measure out my starting amount of iron. I measure out my total iron oxide product. I compare the two. That's my mass percent. But in the absence of that, what I can do instead is I can do a calculation based upon the theoretical values given to me by the periodic table of elements. So the total mass of element X, in this case we're looking at iron, would be the molar mass of iron divided by the molar mass of the whole thing multiplied by 100%. Molar mass of iron, I can pull off the periodic table, 55.85 grams. Molar mass of iron oxide would be that same 55.85 grams, plus the mass of oxygen, 16. So if I add those two together, 55.85 plus 16, I get in my denominator 71.85 grams multiplied by 100%. So 55.85 divided by 71.85 multiplied by 100% to four significant figures would be 77.13% iron. Now we could do a similar calculation for the oxygen in iron 2 oxide and come up with the mass percent of oxygen in that way. However, since iron and oxygen make up the entire thing, we can also do this. Percent of oxygen is equal to 100% minus the 77.13% that is iron, and we get 22.87% oxygen as a result. So this kind of calculation works for any compound that we can think of. What we have to make sure that we do is we have to make sure that when we encounter them, we make sure that we account for all of the elements in that particular substance. So just as an example, if I were to do the mass percent of the other oxide, I'll do that one here in purple. What it would look like instead of this, it would be 2 irons, because my chemical formula has 2 irons in it, divided by 2 irons and the 3 oxygens. So it'd be 2 times 55.85 plus 2 times 55.85 plus 3 times 16.00. So my numerator would be 11.70 grams. My denominator would be that plus 3 times 16 for a total of 159.70 grams multiplied by 100%. The mass percent of iron in that circumstance in this case, the 5 significant figures, 69.944% iron. So there is a difference there. Mass percentages are actually one of the ways that we can help to identify differing compounds of the same elements from each other. We can also use mass percentages to do something else that's really important, and that is we can use it in an elemental analysis kind of circumstance to help us figure out what the compound is in the first place. And that's where this comes in. Empirical formulas. Empirical formulas represent the lowest, smallest whole number ratio of one element to another in a compound. Now, on the previous slide, the FeO and the Fe2O3 both represented empirical formulas. There was no way possible to reduce those down to a simpler whole number fraction ratio without resorting to decimal numbers. Molecular formulas, on the other hand, represent the actual formula of the compound under study. Now, sometimes the empirical formula is the molecular formula. They both are there. Other times, especially when we start to look at organic kinds of compounds, what we will find is that the molecular formula is some sort of multiplied version of the empirical formula. And the way that we tell how much to multiply the empirical formula by to get to the molecular formula comes from this ratio calculation, where I take the molecular mass of the substance, whatever it is, has to be known to us in some way, and we divide it by the mass of our empirical formula. And the number that comes out of this calculation is always a whole number. 1, 2, 3, 4, 5, whatever. But it's always a whole number, never fractional. But what that number tells us is it tells us what do we need to multiply our empirical formula by in order to get the molecular formula. Where this fits into that idea of mass percent is we can use mass percents to give us that whole number ratio of one element to another. The way that we do that is this. We can take those percents and convert them into grams by assuming that we have 100 grams of the compound. Doesn't matter if we do or not. What matters is basically we're going to take that percentage and turn it into grams. And then it starts to resemble what we just were working on before. Grams get turned into moles. And then we use the number of moles of each kind of element to figure out what the whole number ratio is. So we're going to end today with a practice problem. And then when we pick up again with this on Monday, we'll do a couple more practices just to kind of make sure that we have it. And then we'll move on into chapter 3. So the question here is this. What is the empirical formula for an iron oxide compound that is 69.94% iron, 30.06% oxygen? So if we go through our steps, our first step is to turn the percents into grams and then the grams into moles. Well, to turn percents into grams, 69.94% becomes 69.94 grams of iron, 30.06 grams of oxygen out of that 30.06%. Our next step is to convert those grams into moles. Well, we already know how to do that. We can use the molar mass. 1 mole of iron is equal to 55.85 grams. If I do that calculation, 69.94 divided by 55.85, 4 significant figures, 1.252 moles of iron. For the oxygen, 16 grams for every mole. So 30.06 divided by 16 gives you 1.879. So when we get to this stage, sometimes it's very easy to see the mole-to-mole ratio. It'll be very clear that one is double the other, or that they are actually the same. In this situation, can't really tell. So since we can't really tell, we're going to do something to try to put them on more even terms. And the thing that we're going to do is we're going to divide by the number that is the smallest. Now, the reason we divide by the number that's the smallest is it guarantees then we're going to get at least one whole number out of this. Divide a number by itself, it makes the one that is the smallest 1, and everything else is some sort of subset of 1. 1.879 divided by 1.252. Number's 1.5 now. Still not a whole number, but it's a fraction we can recognize. So I got to get rid of the fraction, which means I'm going to multiply both of these by 2. So I get 2 irons and 3 oxygens. The empirical formula is that whole number ratio, Fe2O3. So as far as empirical formulas go, this is what you have to do. And it follows the same process every time. Convert the grams into, convert the percents into grams, convert the grams into moles, compare the moles to each other, and get it down to a whole number ratio. Now, what if you weren't given percentages? Well, actually, that's pretty easy. If you're already given grams, you don't need to worry about the first step. You just immediately convert them into moles and do the comparison. So in your post-lecture homework tonight, I want you to give these a real good shot. Try them out, and on Monday, we'll pick up with a couple more examples before we move on into chapter 3. Have a great weekend.